Naturally, eyes first turned toward the Nevada. She was still afloat, but now her bright color was dimmed by a heavy coating of soot. That the bomb had missed the intended 0 point was soon obvious. Instrument measurements later showed that it had burst 710 yards short and to the left of the Nevada's foremast. This error was far greater than had been thought probable, nearly 4 times greater than the average error maintained in practice bombings. Exhaustive analysis of available photographs and other data has been made, but this analysis has not accounted for the error. A major bombing error was not completely unexpected. The target array and instrumentation were so devised that the location of the burst did not nullify the results of the test as far as graded damage was concerned. Protective margins allowed in positioning the ships and in distributing the instruments achieved recording of graded damage despite the magnitude of the error. The miss did prevent optimum functioning of many instruments. A line of sonobuoys designed to telemeter wave height was rendered useless. The projected 0 point was closest to the Gilliam, an APA. The Gilliam was one of the principal instrument-bearing target ships, and her loss had not been anticipated. She had been only 65 yards from the spot directly beneath the explosion. Within 1 minute after detonation, she sank. So badly ruptured, crumpled, and twisted was she that divers later found her barely recognizable as a ship. 4 other ships were mortally damaged and sank before re-entry or a short time later. These were the Carlisle, another APA, 430 yards from 0 point, the destroyer Anderson, 600 yards, the destroyer Lamson, 760 yards, and the new Japanese light cruiser, the Sakawa, which had been 420 yards from the center of the explosion. Heavily damaged and torn along the center line at the stern, which had faced 0 point, the Sakawa remained afloat for 25 hours before she sank. Of the 5 ships sunk, all had been within 760 yards of the center of detonation. The most conspicuous wreck still afloat was the USS Independence. Only the stamina which naval engineers had built into her as the first of the cruiser hull carriers allowed her to survive. Only 560 yards from blast center, she experienced a succession of serious fires and low-order explosions which rapidly developed aboard her. In heavy seas, she would have suffered progressive flooding from lack of water tightness above the waterline. Her military efficiency was virtually non-existent. Her bulkheads were buckled. Her hangar deck was a jumbled heap of rubble and ruin. Her warped flight deck was gashed and rent and had a crazy tilt. Both elevator platforms had been blown overboard by pressure trapped between decks. Nevertheless, her engines and boilers were relatively undamaged, and guided by tugs, she moved under her own power to a position for Test Baker. Even closer to the detonation, at 400 yards, was the submarine Skate. Demolished was her light superstructure, but interior damage was not sufficient to prevent her from getting underway. Yet her efficiency as a combat ship had been seriously impaired. Her radio and radar antennas were gone. Both her periscopes were inoperable. Her pressure hull proved how rugged are all ships of this submersible type. This inner strength hull was not substantially damaged, and no flooding resulted. She had been closer to the burst than 4 of the ships sunk. The stern of the Nevada was 615 yards from 0 point. Her superstructure was distorted. Her fire control antennas were beyond possible use. A portion of her main deck was dished in. Side casing panels on all of her boilers had been blown out. She needed steam to operate her power plant, her steering gear, and other equipment. This meant that it would be 24 hours or more before she could get underway at the slowest of speeds, even if a combat crew were aboard to perform the multiple tasks of repair. In an instant, her military efficiency had been destroyed. The Pensacola, 700 yards from point of detonation, would have required a voyage to port for extensive repairs before she would again be a fighting unit. Instruments revealed that she had been subjected to blast corresponding to a wind velocity of 384 knots. She had lost water tightness above the second deck, and her longitudinal structural strength had been slightly impaired. Her stacks were ruined, and her topside hatches had failed. Casings had been damaged in all 8 of her boilers. 3 additional ships had been immobilized, principally because of damage to boilers, superstructures, and stacks. These were the Arkansas, 620 yards, the Salt Lake City, 895 yards, and the Hughes, 920 yards from 0 point. Not immobilized, but suffering serious loss of military efficiency were the concrete YO-160 at 520 yards, the Crittenden, an APA, 595 yards, the ARDC-13 at 810 yards, the Dawson, an APA, 850 yards, the destroyer Rhine, 1,012 yards, the destroyer Talbot, 1,165 yards, the LST-52, 1,530 yards, and the Saratoga, 2,265 yards from 0 point, seemingly unscathed except for minor secondary fires. Yet the Saratoga's vital plane elevator had been jammed by the hammer-like blast from above. This indicated extreme vulnerability of elevators on old carriers to such form of attack. 9 other ships suffered moderate loss of military efficiency. They were the Nagato, 790 yards, the Brule, 990 yards, the YOG-83, 1,035 yards, the Banner, 1,190 yards, the Prinz Eugen, 1,195 yards, the Barrow, 1,340 yards, the New York, 1,545 yards, the Pennsylvania, 1,550 yards, and the Butte, 1,990 yards. In summary, every ship within a half-mile of 0 point had either been sunk or had suffered serious loss of military efficiency. Military efficiency of ships as far as 1,500 yards was impaired. One thing was clear: no pinpointing was necessary for a bomb of this type to wreak major damage. Naval experts studying the crippled ships readily saw that here lay a serious challenge to modification and redesign. It was to exposed surfaces and superstructures that the high-velocity air blast wrought its worst havoc, with destroyers proving the most vulnerable. Orientation to blast had important effects. Blast, reflected or focused into passageways and structural pockets, scored heavy damage. Reduction of damage from both blast and flash heat by even light shielding afforded an interesting study. In most cases of radar antenna damage, impairment was so great that repair work could not be accomplished at sea. Boiler damage meant reduced speed and impaired operation of ordnance and machinery. Significantly, the boilers of the modern carrier Independence were undamaged at 560 yards, although all 4 of her stacks were demolished. In general, modern boilers with double casings withstood the blast. Boiler vulnerability proved to be related to stack height and construction. Modern stacks of welded construction fared much better than older riveted stacks. Old boilers of American design proved extremely vulnerable to atomic blast. All of the old United States battleships suffered serious damage to boiler casings and brickwork. Strangely, the Nagato's boilers were unscathed. Damage to the Pensacola involved not only major boiler damage, but incipient failure of main hull structure, as evidenced by damage to main strength column supports in the engine room and the fire room. Her sister ship, the Salt Lake City, also had major boiler damage. The newer Prinz Eugen's boilers at 1,195 yards were undamaged, and the main visible damage was to superstructure. Even when stacks were damaged without accompanying boiler damage, the boilers could not be operated until repairs had been made or emergency stacks built. This meant immediate crippling of ships through loss of power. Extent of damage from blast down the stacks of a ship under full steam can only be contemplated. Electronic equipment was seriously damaged up to 1,200 yards and slightly damaged up to 2,500 yards. Principally, major damage was to wire radio antennas, bedspring-type antennas, and radar reflectors of light-gauge metal. Vacuum tubes and other delicate components remained generally undamaged by blast effects wherever they were securely shock-mounted. Metal tubes fared better than glass. Small, compact electronic equipment fared better than large equipment in resistance to the blast. Shock mounting, shielding, and streamlining proved their value. Within a radius of 900 yards of detonation, electrical equipment and instruments exposed topside suffered severe damage. In general, damage to electrical equipment was not one of the chief factors contributing to loss of military efficiency. Ordnance equipment on exposed vessels suffered little severe damage, although fire control systems were seriously affected by the loss of radar antennas. Optical systems stood up well. Modern rangefinders, normally rugged and shockproof, withstood the explosion with no internal damage. Range keepers, too, suffered light damage only. All exposed ammunition, as well as that in magazines, withstood the heat and blast virtually without change. Torpedoes, mines, and depth charges were not detonated. 12 torpedo warheads on the Independence, while not exploding, were consumed by the fires aboard and gave the flames new impetus. It was possible there was an ammunition or pyrotechnic explosion aboard the destroyer Anderson before she rolled over and sank. Packaged ammunition exposed for special testing remained undamaged at distances greater than 1,000 yards. Pyrotechnics in thin cases but otherwise unshielded were unaffected beyond 1,000 yards. Wrapped propelling charges and mortar powder increments in plastic cases, however, were damaged at distances up to 2,100 yards. Fuel and ammunition loadings for Able Day had been the subject of much discussion when the target array was planned. No fuel or ammunition fires occurred as the result of the burst. Fuel and ammunition loads varied from 15% to full. To prevent spreading of fires and loss of valuable instruments and experimental animals, vessels in the upwind sector carried the lighter loadings. Extending to the outer margins of the array, 27 fires had broken out aboard target ships at intervals after detonation. These fires were in exposed locations. All were extinguished by salvage crews except that aboard the Independence, which burned itself out. Many fires within 1,500 yards of zero point were snuffed out by winds associated with shock wave. Others smoldered for long intervals before bursting into active flame. Burlap wrappings of Army quartermaster material was a frequent source of fire. Jute and manila cordage burned readily. Induced heating from metal parts surrounded by combustibles caused scorching or fires. Scorch marks were found on combustible material on virtually every ship. Color, gloss, and reflectivity were definitely related to the inflammability of such material. Strikingly, fires were of much less importance in overall damage than they had been at Hiroshima and Nagasaki. Humidity differences, the presence of the cloud chamber effect, and the fact that ships are fundamentally fireproof were contributing factors. Fires in the sterns of the Sakawa and the Independence did create serious damage to these vessels, but not many other fires gained comparable headway. Salvage crews extinguished many blazes, but there were fires still burning when the sun went down on Able Day. No oil fires started in the water, although such fires had been feared. Seepage of oil did not commence until passage of the blast wave. Army tanks and heavy guns and mobile equipment suffered no impairment of operational efficiency beyond 600 yards. Unarmored vehicles, searchlights, and aircraft structures were damaged severely at ranges up to 1,200 yards, with minor damage as far out as 2,500 yards. Plastics were susceptible to the heat flash, which caused warping, fusing, and bubbling. Disintegration of laminations occurred where plastic bonding material had been used. Exploration was made of the degree of affinity of concrete for radioactivity and of resistance of concrete to blast. Baked paint in thin single layers on Army equipment withstood the heat of the blast much better than multiple layers of flat paint on decks and bulkheads. Ranges of scorching and blistering were irregular. Thermal screening by steam or fog undoubtedly contributed to this irregularity. Baled and packaged clothing was damaged by fire several miles from zero point. Food packaged in metal or glass containers exposed at 500 yards was cleared for consumption 4 days after Able Day. Heavy rubber behaved well. Pneumatic tires and electrical cables were virtually undamaged beyond 600 yards. Thin rubber coatings and objects of sponge rubber were often badly charred. Experimental animals and their varied reaction to atomic explosion were objects of immediate study. Approximately 90% of the test animals were recovered alive. Some had been killed by indirect blast effects or lost in ship sinkings. In many cases, hair of the animals came out in patches. Male animals showed hemorrhage into the reproductive glands. One misfortune which resulted from the large bombing error was that no animals were in sheltered areas within 650 yards range. For this reason, no data on the effects of intense neutron radiation were obtained. Various experiments were attempted to preserve the lives of animals. Some animals lived for a long time. This increased survival may have been the result of treatment or due to the great biological variation in survival which occurs among all animals. The most successful treatments were penicillin injections and multiple blood transfusions. Blood counts were taken and tables of comparative figures compiled. Of pigs exposed within a 1,000-yard radius, 50% had died by August 1946. In the same radius, 85% of goats and 75% of rats exposed were dead. Differences in animal mortality were partly due to differences in shielding provided the different groups. 15% of pigs and rats outside the mile radius were dead by August. Only 5% of goats in this area on the fringes of the target array were dead. Pathological studies of organs of animals killed by the blast or victims of radiation were carried out with painstaking detail. Color transparencies were made at various stages to preserve medical data. Hemorrhages, ulcers, inflammatory reactions, and other injuries gave graphic evidence of the serious consequences of irradiation illness. Hearts, brains, lungs, livers, kidneys, stomachs, and intestines all showed irradiation effects. It was from such pathological examinations that the fatal results of acute radiation illness were demonstrated. For about 1 month, mortalities from radiation injuries continued to mount. Evidence indicated that thermal radiation would produce serious burns on exposed personnel up to about 1,700 yards. Exact distances would vary markedly with atmospheric conditions such as the presence of dust or humidity. At lesser distances, slight shielding would protect against burns, but death might result from ionizing radiation. A few animals within the lethal radiation zone were protected by shielding and survived. While an exposed person at about 1,200 yards would probably die, a well-protected person might be as close as 600 yards and still not receive a fatal dose. Experiments show that the gamma radiation is reduced 50% by 1.25 inches of steel. 9 inches of steel would reduce intensity to but 1%. Neutron radiation within 650 yards is an even more deadly killer, and light steel shielding affords little protection. At these close ranges, however, the general blast effects are so tremendous that neutron and gamma radiation, deadly as they are, become superfluous lethal factors. Animals exposed to atomic explosion became hyper-irritable, showed loss of appetite, muscular weakness, diarrhea, and increased rate of respiration. The direct injuries caused by air blast alone were hemorrhages in the lungs and in the bowels, the air-containing portions of the body. Following Able Day, the animals were intensively studied. The data obtained has helped to clarify the knowledge of atomic bomb injuries. The import of what medical men learned is of great significance. More than 50% of the animals situated within a half mile of 0 point had already died or were soon to die. Between 15 and 30% of the animals exposed at distances from a half mile to a mile from detonation perished. A small percentage of the animals outside the radius of 1 mile also died. As days went by, the death toll mounted. From the animal studies, important conclusions could be drawn. At close range, death to exposed personnel would be instantaneous and due to multiple causes. The air blast wave and thermal radiation would be most effective against exposed personnel up to 1,000 yards. But at even greater distances, the thermal radiation would produce loss of military efficiency through burns to exposed skin, and the air blast wave would produce indirect injuries such as those caused by flying missiles or impact against bulkheads or stationary objects. The chief cause of death outside the 600-yard radius would be ionizing radiation. Gamma radiation would produce serious injury at great distances, even in personnel protected from blast by a thin layer of steel. By the end of November 1946, over 1,666 of the 3,619 animals exposed to the blast were still alive, roughly 43%. If they had not been killed for study, 351 more animals would also have survived. Generally, there was no persistent radioactivity after the test, and examination of the ships by various groups was not seriously delayed.
From an operational standpoint, Test Able was considered very successful. Graded damage had been produced to meet requirements. Instrumentation had been good, and a mass of important data had been accumulated. A basis had been established for determining the vulnerability of ships and men. Conclusions could be substantiated with abundant evidence. The effectiveness of the bomb was now more specifically known. It had become a measurable quantity. No longer was it a mythical agent of supernatural power. In the summary of the Able Day damage alone, impressive though this damage appeared to be, it was apparent that the full significance of the test could not be manifested. Amid the sober reflections, there was an occasional humorous note, and crews of surviving ships were not above advertising the hardihood of their vessels in the face of atomic blast. While the press of the world was hashing over results of Able Day, Joint Task Force 1 began preparations for Baker Day, a test of atomic explosion under the sea. Much remained to be done. There had been 4 air explosions. This was to be the first detonation beneath the surface. Damaged ships had to be photographed, cleared of debris, and repaired. New instruments set out and difficult diving operations completed. The target fleet had to be redisposed. Extensive preparation was required for handling and detonating the bomb underwater. Instrumentation for this test would be less handicapped, since the point of detonation was accurately fixed. The Baker Day bomb was to be lowered from a landing ship, the LSM-60. This vessel had been modified to provide radio transmitting and receiving apparatus, a laboratory for bomb assembly, and rigging apparatus to lower the watertight caisson in which the bomb was to be enclosed. This bathysphere was fitted with a coaxial cable for transmission of ultra-high frequency signals. Sensitive relays aboard the LSM would be closed by tone-modulated signals. These signals, in turn, would close heavier relays, controlling the power supply to the arming and firing circuits of the bomb. To avoid error, a repeat-back system was installed. The relays, upon being closed, operated oscillators which provided the repeat-back signals. These signals modulated a high-frequency transmitter, which sent signals to operate lights on a registering panel aboard the Cumberland Sound. An additional repeat-back circuit was used to verify closing the arming voltage circuit of the bomb. In rearranging the target array for Test Baker, it was known from the results of the Able Day burst that few ships within 500 yards of the bomb could survive. The Saratoga and Arkansas were placed within this range and broadside to 0 point, but their size precluded mooring other major ships close by. Submarines were to play an equally important part in the second test. Submerged, they were to gauge the effects of underwater blast on modern hull design. In all, 88 hulls were exposed. The general spiderweb plan was again used, with the LSM-60 as the central ship. In the allocation of the 5 battleships, the nearest was the Arkansas, placed just 200 yards from the caisson. The other battleships were at 800, 1,000, 1,100, and 1,200 yards from 0 point. Because of predictions of what would happen in the underwater blast, Admiral Blandy decided to moor the Saratoga 500 yards from 0 point to prevent her from sinking too rapidly after the blast. This was done to permit photographic analysis of the behavior of her flight deck under severe hull pressure and tremendous wave action. Slack moorings, however, allowed her to drift when the wind changed on the morning of the blast. She was but 350 yards from 0 point at detonation. The battered Independence was moored at 1,200 yards. Two cruisers were exposed end on, one at 700 yards and the other at 1,200 yards. The Prinz Eugen was at 1,970 yards. 8 destroyers were placed along a curved line at distances from 850 to 3,500 yards. 3 other destroyers broadside to the explosion were at 700, 1,250, and 1,750 yards. The submarine pilot fish of heavy hull design was placed 260 yards from the blast. 2 pairs of submarines, one light-hulled and one heavy-hulled per pair, were placed at 800 yards and 1,300 yards. 2 more heavy-hulled submarines were placed broadside to the blast, one at 750 yards and the other at 1,200 yards. And a light-hulled submarine was placed broadside at 1,800 yards. 6 of these submarines were submerged just before the test. A floating concrete dry dock was placed at 1,200 yards, and 2 concrete barges were moored at 800 and 1,000 yards. 17 APAs extended in 2 curved lines from 0 point. One line end on from 500 to 3,700 yards, and the other broadside from 700 to 3,200 yards. 33 landing craft were used. 4 LSTs extended in a single line from 1,700 to 4,100 yards. One had a floating bridge tied astern. 1 LST was end on at 750 yards. Another was placed on Bikini Beach. A line of 5 LCTs and a line of 4 LCIs were arranged at distances of 2,000 to 4,000 yards from 0 point. 4 LCTs, 5 LCMs, 6 LCVPs, and 2 LCILs were also zoned along the beach at intervals of 100 yards to simulate an amphibious force making an invasion. Oceanography was more significant in the underwater test. Studies of currents in the lagoon had been used to predict the spread of radioactive areas following detonation. Ocean water normally flows into the lagoon continuously over the eastern and northern reefs. Outflow occurs principally through NU Channel. Dominant features of water movement inside the lagoon are a wind-driven surface current flowing in a west-southwest direction and a return current at the bottom. Water transfer is very slow. It normally requires 25 days to exchange 1/2 of the lagoon water with ocean water. Velocities of currents at different depths were determined, and the direction in which the currents veered was recorded. The average drift of the upper 15 feet of water over periods from 8 to 36 hours was determined by current poles. Frequent observations were taken. At night, radar reflectors were invaluable. Dye markers were used primarily in channels and over reefs where other methods were not practical. Variations of temperature and salinity were studied. These studies clarified certain obscure results of current measurement by normal methods. Data collected enabled scientists to determine the path of contamination in the lagoon and the rate at which the lagoon would be flushed. This information was important in planning details of the operation relating to the safety of personnel, methods of approach to target ships, and placement of vital instruments. Thus, it was known in advance that by the end of Baker Day +1, the strip of contaminated water would reach Bikini. Accordingly, since access to the land areas would later be denied, plans were laid for the early rescue of instruments by helicopters and by landing parties.
July 25th had been set as the tentative date for Baker Day. Once more, attention was focused on weather. Long-range forecasts were good. Preparations for the test went ahead with all possible speed. Then came a threat of upset. An equatorial front moved northward toward Bikini. Thunderstorms and showers developed. By the day before Baker Day, it was still raining. Faces were glum. Tasks still to be done were made more difficult by the downpour. But Crossroads' famed luck was holding up. The front swerved to the northeast. Drier air invaded Bikini. Good weather would prevail. Cloud cover would be at a minimum. Surface winds would be only 7 knots. Visibility would be excellent. Baker Day was set, July 25th, 1946. Evacuation of target ship personnel began immediately. A general exodus commenced as the Sidor steamed out of the lagoon. Last-minute submerging of the unmanned submarines began. Crews had spent many long hours of preparation for this work. After the pilot fish had been submerged, her radar mast popped above the surface because of a shifting of exterior ballast. It was now too late to reballast. Similar difficulties were encountered with the Sea Raven. Her bow and her periscope shears were showing, but after much work and the loss of one suspension anchor, total submergence was achieved. At 0524, the Mount McKinley began to move out of the lagoon, now presumably clear of all personnel. But a last sweep with binoculars revealed emergency bunting flying from the yardarms of the Gasconade, a target APA. Aboard her were a group of last-minute personnel who, through oversight, had not been evacuated. Their signals were espied, and they were hastily removed to safety by the conserver. The lagoon was clear by 0620. Aircraft were already aloft as air components moved into position. Reports were streaming back from weather reconnaissance planes, which were making far-flung weather sweeps north and east of the lagoon. 2 command aircraft were on station at dawn. At 1-minute intervals, 7 F-13 photographic aircraft soared into the morning sky, followed by 2 C-54 photoplanes. F-13 altitude for the Baker mission was 15,000 feet. The overall flight plan was similar to that on Able Day, except that the photographic orbits had been moved into 7 miles slant range as against 12 miles on Able Day. 1 F-13 was assigned to a course which would bring it directly over the target at 30,000 feet to make vertical photographs at the moment of detonation. 1 C-54 and 2 B-29s carried press and radio reporters and news photographers. A PBM bore aloft the President's evaluation board. Another PBM carried the radiological safety and technical observers who were to report early results. Army and Navy drones and reconnaissance aircraft soar into position. As Howe Hour approaches, 32 Army aircraft and 29 Navy aircraft are weaving through the air pattern. Mapping planes are making their last-minute runs over the target area. Scanning summaries of the air operation, General Kepner reports ready to the task force commander. Watches are consulted. Radio silence is imposed upon the task force. The bomb is being armed by radio control from the Cumberland Sound. Eyes turn toward the LSM-60. 90 feet below her and halfway to the bottom hangs the caisson which encloses the 5th atomic bomb. The caisson swings gently in the current, like a cradle rocked in a subsurface wind. Grim silence has settled over the lagoon. On the Cumberland Sound, automatic controls have taken over. Panel lights flicker. Transmitters hum. Tension grows. Perspiration beads foreheads, though the room is air-conditioned. Time now is measured in seconds.
10, 5, 4, 3, 2, 1, fire!
A flash of yellowish light, and the lagoon erupts as if the earth beneath is disemboweled. Up goes a geyser like 1,000 Niagaras in reverse. 400,000 tons of water rising vertically against the pull of gravity, scattering fragments of the LSM-60 over the lagoon. As it rises, the column cascades outward into a spiked cauliflower. Then collapse begins. At 1 second, the column has reached 4,100 feet. At 60 seconds, 7,600 feet. The crown of the cauliflower curves outward and down, shadowing the target array. This is the derby hat phase. As the column plunges back to the sea, a surge develops at the base of the column, and a wall of spray, foam, and poison fog sweeps outward at the initial rate of 60 knots, an unpredicted phenomenon. This is the most poisonous fog that mankind has known since the dawn of creation. It contains residual plutonium. Whirling and seething, the fog dwarfs and engulfs the vessels, and for a time enshrouds the lagoon. This surge reached a height of 2,000 feet and extended over a radius of 8,000 feet. The rain and mist covered an area of 15 square miles and was lethal over an area of about 9 square miles. Slowly, winds carried the murky cloud to the northwest. For an hour, it was readily observed. At the end of 2 hours, it could no longer be distinguished from the normal cloud mass on the horizon.
Gigantic waves had been created by the explosion. These were 94 feet from trough to crest at 300 yards from 0 point, and 9 feet from trough to crest at 2 miles. The first wave raced out at 45 knots, rocking the entire fleet. Bomb-produced surf was clearly visible to orbiting planes. Although these waves represented less than 1% of the bomb energy, they contributed significant damage to at least 5 of the target ships. Between the base surge and the radioactive rain which fell on the lagoon from the cloud, all but 9 of the target vessels were alive with contamination immediately after the blast. Witnesses searched for adjectives to describe the might of this explosion. They had no precedent with which to compare it. One fact alone stunned the imagination. The blast had produced an 1,100-yard circular crater 25 feet deep in the floor of the lagoon and had flung up over 2 million cubic yards of bottom material. After the blast, there was a layer of mud and sand several feet thick on the bottom of the lagoon in the neighborhood of the detonation point. The condensation cloud gave the blast a momentary appearance of a birthday cake on a platter. This condensation stage lasted but a brief moment. By 4 seconds, the cloud had reached maximum size, roughly 1 mile in diameter. At 18 seconds, it became ring-formed and began to stratify. By 30 seconds, it had vanished. The amount of energy released was normal for a bomb of the Nagasaki type, comparable to the energy released by the explosion of 20,000 tons of TNT. Drone performance was even more satisfactory than on Able Day. All drones and mother planes were jolted as if by a close burst of flak. The B-17, which was flown over the burst at 6,000 feet, was battered by the shock wave, but completed its flight and landed safely. Its bomb bay doors were warped. All inspection plates were blown open. The tail gunner's escape hatch was blown inward. The canvas boot over the tail wheel was split. Study of the flight analyzers revealed that this aircraft underwent reactions never before explored in flight. The air shock wave at 6,000 feet was approximately 1.9 pounds per square inch, lasting more than 1/2 second. Another drone at 16,000 feet was over the target center 2 seconds after detonation. Its cameras, aimed vertically, produced an interesting record of the burst. The air shock wave at this altitude is illustrated by the severe shaking of the aircraft, which stopped the camera. Engine operation of the drones was not noticeably affected. Radio control, even during moments of the blast itself, was not affected at the distances studied. Far less radioactive material was present in the air than after the Able Day explosion. One B-17 drone landing at Eniwetok was slightly damaged when wind conditions and brake trouble caused it to run off the end of the runway and over an embankment to the coral shelf. Damage was not severe, and recovery of instruments with recorded data was complete. Within an hour, the first radio-controlled drone boat was sent into the target array to collect water samples. As the drone boats returned from their sampling missions, crews hosed them repeatedly to wash off radioactive spray. The drone boats were used for radiological surveys for 2 days after detonation. They could go with impunity where man still dared not venture. Meanwhile, salvage crews and instrumentation teams had entered the target array to collect the recording instruments which had been set out. Film from the towers was recovered and rushed to processing laboratories. Boarding teams removed animals from target ships under difficult conditions because of time limits imposed by radioactivity.
As reports filtered back from inspection crews, early estimates of damage were made. The LSM-60 directly over the bomb had completely disappeared. The 26,000-ton Arkansas, moored 200 yards from 0 point, had capsized and sunk within the first minute after the blast. She settled upside down on the floor of the lagoon. Divers found her bottom sieved with holes, her side shell plating broken at many points. Rivets had failed at seams and butts, and her hull was indented as much as 6 feet in some areas. Virtually all her damage was below her waterline, a characteristic of Test Baker. The Saratoga had been 350 yards from 0 point. She had suffered no severe structural distortion or hull ruptures, but she was sinking from progressive flooding through leaking rivet seams. The forward half of her stack lay across her flight deck. The stacks, surviving the blast, were carried away by mass movement of water. Shortly, she developed a slight starboard list. No salvage crew could approach. Radioactive death lurked everywhere. Not even a pelican hook could be attached to her anchor chain to tow her to shallow water. It was the death of a gallant warrior, bleeding oil in great gushes which spread over the lagoon. Her guns now silenced forever. 7 times the Japanese had announced this ship sunk. Difficult now to watch was the death of old Sarah. After 8 hours' struggle, she gave a final lurch, straightening herself for the grave. At 16:16, she slipped beneath the surface, leaving a lonesome gap against the late afternoon sky. The Japanese battleship Nagato had begun to list to starboard and settle by the stern shortly after the explosion. She had been moored at 745 yards and was flooding progressively. By a quirk, one of the mooring buoys of the capsized LCT 1114 had been cast up on her deck by the blast. She was radiologically unsafe to board, and though salvage crews begged to take on the job of damage control or beaching, permission was denied. On the 4th day, when her doom was certain, orders were issued to be prepared to torpedo her next day as a test of new torpedoes. But she spent her last moments alone in the moonless night, unseen. When morning came, she was gone. Air bubbles told where she had sunk. 3 submarines sank in the explosion. The pilot fish went down, nearly all compartments flooded, the tops of her ballast tanks no longer tight, and her superstructure dished in. She had been 260 yards from 0 point. Divers recovered vital instruments that had been attached to her deck and bridge. The skipjack, at 800 yards, went down with a crack in her athwartship plating above one of the torpedo rooms. Later, she was raised and returned to San Francisco for detailed study. Her forward battery compartment and her control room were flooded, and the tops of her ballast tanks leaked. The Apagon, at 845 yards, sank in deeper water, with most of her compartments flooded. Her conning tower hatch and several bulkheads had failed, and a tank top was ruptured. Divers found a hole through the pressure hull forward. A fourth submarine, the Dentuda, submerged at 1,500 yards, had settled to the bottom from flooding that a crew could have controlled. Raised, she had to be beached. Damage to other submarines was not significant, although raising them called for solid seamanship by divers, salvage workers, and deckhands. Exteriors of all the submarines raised required decontamination. Submarine hulls proved their ability to absorb much damage. Nevertheless, submarine batteries, although shock-mounted, proved seriously vulnerable. The concrete barge YO-160 sank immediately. Another small craft, the LCT-1114, was capsized by the burst. Her bottom showed no evidence of damage. Demolition charges were used to sink her. 5 ships were immobilized by the blast. The Fallon, nearest of the APAs to the explosion at 500 yards, had her shell and bottom wrinkled, her decks buckled, her hatches dished in, her boiler foundations stressed, and her air casings ruptured. On the Fallon, as on several other ships, radioactive coral sand from the lagoon bottom and fragments apparently from the LSM-60 were found. Beached with the Fallon was the destroyer Hughes, which had flooded through fractured sea connections and piping. At 635 yards, all her boilers were badly damaged. Her main engines were inoperable. Wave action had damaged topside hamper, and 2 torpedoes hung precariously from her deck tubes. The Gasconade, 580 yards, flooded her engine spaces through broken saltwater lines, but she remained afloat. Her shell was wrinkled, her hatches were dished in, and much electrical equipment was damaged. The cruiser Pensacola, crippled by the air burst, was the largest ship immobilized by the underwater burst. She was 640 yards from 0 point. Her boilers were badly damaged. 3 of her main battery mounts were inoperable. Propelling and auxiliary machinery was seriously damaged. Hull damage added to the destruction. Shell plating was dished in, and bulkheads and stanchions were deranged. She was kept floating only by difficult salvage operations. The LST-133 was rendered immobile by damage to her main deck, hull, and ballast tanks. Flooding made her machinery inoperative. 5 ships suffered serious loss of military efficiency. 3 of these were battleships. The New York, at 820 yards, suffered minor flooding from opened seams in shell plating and tanks. 3 turrets were inoperable from fractured holding down clips. 2 boilers were temporarily useless, and her fire pumping system and a diesel generator were rendered inoperable. The Nevada, at 1,030 yards, suffered damage to her main steering unit and diesel generator. The holding down clips on one main turret were sheared off, making the turret inoperable. Much dished-in plating was observed. The Pennsylvania, at 1,200 yards, suffered minor structural failure and leaked through stern tubes and shaft glands. The Salt Lake City, at 1,200 yards, leaked after the heavy hull shock through stern tubes, shaft glands, rudder bearings, and some piping. The destroyer Mayrant, at 815 yards, received damage to bulkheads, stanchions, and weather hatches, plus flooding from broken lines and some boiler damage. In general, surface vessels within 800 yards were either sunk, rendered immobile, or seriously impaired in military efficiency. Slight loss of military efficiency was felt by vessels as far out as 1,300 yards from blast center. The range of major hull damage for typical service combat vessels was approximately 625 yards. The range of minor hull damage was approximately 950 yards. 8 of the 18 target craft on the beach were swamped or partially flooded. 1 LCVP was washed off the beach and sank. Baker Day, however, produced information more overwhelming than the vast extent of ship damage. For the first time, the insidious potentialities of radioactive contamination were fully revealed. These death-dealing potentialities had been predicted. Now they were actual. Months later, lingering radioactive contamination was an invisible menace to any form of life at Bikini. For days, and in some cases months after the tests, monitors carried out extensive patrols of Bikini Lagoon, the target ships, aircraft, the islands, the air, and the open sea adjacent to the lagoon. Shortage of monitors handicapped the work, but by dint of great effort it was accomplished. Data from thousands of radiation recording devices had to be tabulated in these studies. For the first time, detailed studies of radioactive contamination could be made. In previous atomic explosions, most of the radioactive poisons had been carried off in the mushroom clouds. Now, about 50% of these fission products remained in the water where they had been discharged by the blast. Decontamination was a grave problem. Methods had to be improvised to reduce the overall contamination sufficiently to allow collection of instruments and technical examinations. The poisons restricted the movement of men and ships. They made target vessels uninhabitable for long periods. They revealed how a harbor or an entire city could be crippled with silent, unseen death. In Test Able, gamma radiation was dominant. In Test Baker, alpha and beta particles were an added danger. Months after the explosion, target vessels were death traps for human life because of these radiations. Continuous monitoring was necessary to protect workers from undue exposure. Fatalities could occur from ingestion or inhaling of microscopic quantities of plutonium or long-lived fission products. The deadliness to humans is aggravated by their tendency to accumulate in the bones. Radiologists knew that alpha radioactivity from plutonium diminishes very little over periods of years. How to cope with this plutonium poisoning is still one of the chief problems of health physics and of industrial hygiene. Decontamination of dangerous areas requires new knowledge and new techniques employed by large groups of skillfully trained radiological personnel. Gamma radiation in Test Baker differed from similar radiation in Test Able. In Test Able, the period of intense gamma radiation was limited to seconds. In Test Baker, intense gamma radiation remained in some areas for weeks and in others for months. Radioactivity in the water was created by fission products which emitted beta and gamma radiation and by unfissioned plutonium from the bomb which emitted alpha particles. The alpha particles themselves are of low penetrating power, but micrograms of alpha-emitting material within the human body are fatal. Gamma rays readily penetrate flesh, water, and clothing, but are reduced to half intensity by about 1 inch of steel. The cloud and base surge caused a radioactive precipitation 1,800 yards upwind from 0 point and 2 to 5 miles downwind. This rain deposited radioactive material on the surface of the water. Six days after detonation, extremely high radioactivity was reported in the layer of mud and sand on the bottom. Diffusion and convection currents had done their work. Radioactivity would have brought death to thousands of men if personnel had been exposed on the target ships. At 1,000 yards, topside personnel would receive fatal doses within 1 minute. If their ships were immobile or contaminated, they would receive 20 times the lethal dose within an hour. These are grim facts. Topside personnel within 1,700 yards upwind and 2,500 yards downwind would receive lethal doses within 5 minutes. If they sought shelter below decks, the dose would be reduced by more than 1/2, but survival would be a long chance only. Porous materials such as cordage, canvas, and wood were much more heavily contaminated than were metal surfaces. Ships with wooden decks absorbed much more radioactive rain than did ships with metal decks. Closed hatches and ventilators kept much radioactive material from penetrating the interiors of target vessels. When leakage did occur, decontamination problems were serious. Certain below-deck areas on the Salt Lake City read as high as 20 Röntgens per 24 hours, 13 days after the blast. Similar below-deck conditions existed on other vessels because radioactive water had entered through openings resulting from Able Day damage. Submarines being submerged were not subjected to the radioactive rain, so contamination was less than with surface vessels. Bitumastic applied to submarine hulls showed a particular affinity for radioactive products. Decontamination of this porous material, when necessary, was difficult. Target vessels were not alone in exposure to radioactivity. Support ships operating in the lagoon began collecting deposits of radioactive material in their evaporators and saltwater lines. Removal of these deposits presented serious problems, and crew activity had to be carefully monitored. Marine growth and rust spots also favored accumulation of fission products. This situation posed a separate problem requiring attention upon return of the ships to major ports. Fewer animals were exposed in Test Baker, but results were even more striking. Virtually all of the Test Baker animals were dead by 1 November 1946, victims in most cases of gamma radiation. No animals were exposed topside. The animals were placed in the sick bay operating rooms on 4 APAs, the Gasconade, the Briscoe, the Catron, and the Bracken. Death of pigs and rats on the Gasconade, Briscoe, and Catron was caused by gamma radiation which passed through the metal of the decks and bulkheads after emanating from contaminated material which surrounded these vessels. When recovered, the more heavily irradiated animals were already in a dying state, capable of only feeble muscular activity. Others suffered from diarrhea and extensive hemorrhage into the skin and other tissues. Although the greatest amount of shock from the Baker blast was transmitted through the water, the shock wave in the air was equivalent to that from an explosion of 4,000 tons of TNT. Through instrumentation, scientists confirmed that the peak pressure in the water at close distances was greater halfway between the surface and the bottom than it was just beneath the surface. The positive pressure in the water, a tremendous hammer blow against the hulls, lasted for about 2 milliseconds. The negative phases and reflected pulses followed. Underwater pressure was irregular because of different angles of reflection from the bottom of the lagoon. As quickly as possible after Baker Day, technical and scientific groups made their inspections, gathered up their test materials, instruments, and data, and returned to the United States. General homeward movement of the task force soon left only skeleton logistic detachments and radiological survey teams behind. By September 26, 1946, Bikini Atoll was completely evacuated. Entry of unauthorized shipping to the lagoon is still restricted. Many of the target ships remained at Kwajalein for further radiological study. All ships of the supporting force were carefully monitored when they arrived at United States ports. Those that showed residual radioactivity were decontaminated. At the Joint Task Force headquarters in Washington, work of preparing the General Joint Task Force report and more detailed unit reports was accomplished. Scientific analysis was initiated at military installations, universities, technological institutes, and research laboratories throughout the country. Obviously, only data which could quickly be extracted and readily be analyzed could be included in the preliminary reports. But even these soon grew into 30,000 pages of technical matter. They are still growing. Complete evaluation and correlation of significant information will require years. Some results had an immediate practical application. Some groups will continue to be interested in dynamic effects of the explosion, the ship, water, and air motions and their consequences, radiation, shock pressures, displacements, stresses, and distortions. Other groups are concerned with measurement of physical change wrought on materials. These changes include transformations in solid structures, loss of strength, metallurgical effects, absorption of radioactivity, and decline of corrosion resistance or durability. During July and August 1947, a year after the Able and Baker explosions, a comprehensive resurvey was made of Bikini Lagoon. Studies were made of residual radiation, particularly in food organisms. Great attention was given to dangers from alpha radiation. New biological specimens were taken both from the islands and from the surrounding reefs and waters. Deep cores were drilled into the coral to determine atomic effects upon reef-building processes. These cores went almost twice as deep as previous drilling in a Pacific atoll. Divers raised important instruments that could not be previously recovered. The sunken Arkansas, Saratoga, Nagato, Pilotfish, Gilliam, and Apagon were of revived interest. Examination was also made of a portion of the LSM-60. Scientists were particularly interested in types of rupture, heat effects, and radioactivity. For the first time, underwater television was put to scientific use. An underwater camera was lowered over the submarine Apagon, lying in about 160 feet of water. While no new data was obtained by this experiment, the test pointed the way to interesting developments.